Is Petra Schwer from Otto von Guericke University, Magdeburg, and she's going to talk about shadows in Coxeter groups. As usual, I'm going to mute you all, and then if you want to ask a question, unmute yourselves. Okay, thank you, Petra.
Okay, thanks, Ian, for introducing, and thanks for many talks so far. So let's see how this one goes. It's my first virtual talk, and I haven't practiced before, unfortunately, so we'll see. Okay, I'm going to talk about shadows in Coxeter groups, which is a combinatorial object associated to a Coxeter group that has, as I think, very interesting algebraic properties and links to groups in which Coxeter groups appear as Weyl groups, but also to geometric features of the buildings associated to these groups. And we will see a bit of all of this in this talk. Let's start with two questions which you need not understand right now. I just wanted to put them so that you see what kind of questions we're after in this talk. So there's two things, and in the end, we'll even see how these two things are going to be related. So question A is about figuring out whether certain varieties called affine Deligne-Lusztig varieties are on the one side non-empty, and also how to compute their dimension. So these varieties here, they're indexed by two elements, x and b, and these little x and b's, they will be elements of a Coxeter group. Let me try and make this pen a bit finer. All right. And then the other question I want to highlight in this talk is the following: is there an analog of the Schwer-Horn theorem for SLN QP? So the Schwer-Horn theorem is a result for SLN-R or SLN-C, so for the reals or complex numbers. And I'm going to explain what it's all about. It's computing how certain entries of a diagonal matrix change if you multiply by something on the left. So these two questions are directly linked, and we'll also see later how, to the following three pictures on the bottom. So on the left-hand side, you see, well, in all of these three, you see a plane that's triangulated by equilateral triangles. And on the left-hand side, you see a bunch of red dots in a convex region that forms a hexagon. In the middle, you see red triangles in the same triangular tiling of the plane. And on the right-hand side, you see these gray colored in triangles. And the two left-hand side pictures, they correspond to question B. So this would be B. And this one corresponds to A. And the only feature I want to highlight for now is that you can actually find this middle picture, and then also the left-hand side picture, in this right-hand side picture with the gray triangles. So see this ship over here? This little ship appears in several places in this picture on the right-hand side. And as it turns out, this whole hexagon of red triangles can be filled in this right-hand side pictures below these ships. So over here, but also over here, like this. And then the same for this other triangle. So here, for example, it's this little ship itself, but then also the triangles sitting underneath. So this one, for example, and then these two, they would be colored red on the left-hand side, and then all of these like half hexagons sitting in here. They're the half hexagons you see on the left-hand side as well. So the pictures somehow fit into one another, and so do the questions A and B. And at the end of the talk, hopefully everyone will have some sort of understanding how these things fit into each other and are related, and what they have to do with Coxeter groups and how they can be described in combinatorial terms and objects related to Coxeter groups. Okay. Oh no, why is the slide empty? What happened here? Can you see something?
No, I can't see.
Oh, I'm sorry. Somehow. Okay, let me try. Okay, the preview has all the information. So it should be fine. I'm clicking on them now. There we go. Can everybody see the slides now?
Yes.
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 Okay. I don't know what happened. Sorry for this. Okay, let me say a few more words to these questions A and B before we dive into the Coxeter group and combinatorial business. So question A, I said, is about affine Deligne-Lusztig varieties. It's a class of varieties I won't define. It's related to the affine Grassmannian that's related with algebraic groups, say SLN. So think SLN, it's a group that belongs to certain double cosets in SLN. And as I've already mentioned, it's parameterized by pairs of elements in a Euclidean Coxeter group. So most Coxeter groups appearing in this talk will be Euclidean, meaning they're acting as reflection groups on some Euclidean plane with a co-compact action. So we have triangles as their fundamental domains. And then one can prove that such a variety is morally non-empty if and only if this element B is in some shadow of this other element X. So we don't know yet what a shadow is, but I'm telling you up front that they're extremely useful to compute non-emptiness of varieties. And the shadows will be linked to what's called a folded gallery in a Coxeter group, and we'll also see the definition of this. And some statistics on the number of folds and how many steps you do in a certain direction will enable us to actually compute the dimension of this variety as well. So, and this is joint work with Liz Milicevic, who's based in Haverford, and N. Thomas, who's based in Sydney. So the question B, I'd like to say a bit more about, as it's much easier to say some explicit things about this question. I'd like to focus on this. So one example for the groups I'm looking at is SLNR. And as you probably all know, this group can be decomposed in the following sense, that if you pick an element little g in the group G, so in SLNR, you can write it as a product of three matrices, little u, t, and k, where U is a unipotent matrix. And in here, this just means you have a lower triangular matrix with ones on the diagonal and something below the diagonal and zeros above. And then a diagonal matrix, often called the torus. And then some matrix in K, which is here orthogonal matrices. In general Lie groups, it would be the maximal compact subgroup. So here, for n equals 2, you would, for example, see matrices like this with a determinant 1. So C squared plus S squared is 1. And now the question we're after is, you have this decomposition U times T times K, where the K is on the right-hand side. So what happens if you accidentally multiply a diagonal matrix little t by something in K on the left? And then you ask, how does the diagonal change? So what are potential new diagonal entries if you've multiplied a diagonal matrix with something in K on the left? Okay, so since this is SLN, and were able to compute stuff, we could just go for it, take a matrix, say, I don't know, in n equals 2, we take a diagonal matrix, which would look like T 1 over T, and then multiply this matrix. Now I use T twice, that's not good. Say lambda, 1 over lambda. This is our matrix little t. And we multiply it on the left by k, and then we can use the standard algorithm to left-right decompose and write it as some other matrix u times t prime times k prime on the right. And then you just compute what the answer is. And what you'll find is that these t primes are of the following form. They're obviously, again, mu 1 over mu's. And then this mu must sit in between lambda and 1 over lambda. So depending on whether lambda or 1 over lambda is the smaller one, it's bigger than lambda and smaller than 1 over lambda, or the other way around. So this is essentially saying that all you have to do is permute the entries of your diagonal matrix T and look at all the ones that sit in between, but sitting in between is nothing but taking its convex hull. So in general, this first little arrow here, if we're looking at SLN over the reals, will give you all of this convex hull here, where lambda is somehow the entry in R to the n minus 1 that describes the diagonal matrix. So you need one entry less than the size of your matrix, as you have this extra condition of the determinant being 1 that determines the last entry in your diagonal matrix. So you can really transport this into some R to the n and answer the question there. Okay, so on that level, this is a theorem by Horn and Schwer and Horn, but also Thomson, who proved that this projection onto T is really the convex hull of the permuted entries of the diagonal. Constant later generalized this for other real Lie groups, so other types than type A, say, where you have to replace the symmetric group by the respective other wire groups, which is some other finite Coxeter group. And then I proved a generalization for this if you replace the reals or complex numbers by some other field. Yeah, the method that goes into this, and we will actually more or less see a sketch of a proof of this result later, is to somehow mimic what Constant did for the symmetric spaces and replace his arguments that transported this problem about matrices into a question about symmetric spaces to the world of buildings, and run a geometric argument there, which is by nature much more combinatorial than what was going on in Constant's proof. It's also much easier, in fact, I think. Okay, so this is where this is like the background where all of this shadow business arose. And for what comes next, you can start by forgetting what we just talked about, because in order to introduce the shadows, actually define what they are, we don't really need all this algebraic background about the algebraic groups, buildings, Lie groups, etc. We can really focus on the Coxeter groups themselves and just talk about combinatorial behavior within these groups and their associated Coxeter complexes. Okay, so the outline for the rest of this talk is the following. I'm quickly recalling what a Coxeter group is, and we'll then introduce the shadows and also a notion of orientations on Coxeter complexes, which are necessary to define the shadows. I will then afterwards explain how these shadows and the folded galleries one needs in order to define them naturally arise in the context of Euclidean buildings, which then automatically will lead us back to the questions we had looked at in the motivation part, and will provide algebraic interpretations of the combinatorial things we've computed next. And I will end this talk with a bunch of open questions. So if you like shadows, there's a lot to do. Okay. This is really bad. Okay, I guess I have to go slow when I go to the next page in order to avoid the text disappearing.
Yeah, I think it's because your pages have such beautiful pictures on. The computers are struggling to display them, maybe.
Yeah, that could be, I don't know. But I didn't want to leave them out. I mean, once you use the computer, you can actually show all these beautiful pictures. Okay, let's see. Here's a Coxeter group given by its presentation. So you take a bunch of generators. There's not only two, but there's many of them in capital S. And for each pair, you need an integer mij, which describes the order of their product. And then all of them have to be reflections. So you also ask for SI squared to be the identity in this group. Okay, so those are the Coxeter groups in general. And in this talk, for the rest of this talk, all of them will be affine. And as I said, they act on some R to the n. And down here at the right-hand side, we have a two-dimensional example already, which we've already seen. Now, let me just quickly illustrate the properties I've listed here by providing the unique one-dimensional example. So in dimension one, you only have one affine Coxeter group, which is generated by two reflections, S and T, along 2 points in the real line. And then the rest is somehow carried over by these two reflections. So the reflection point of S gets mapped over here by the reflection T, and so does the reflection point for T get mapped over to the left by the reflection S. And if you keep applying reflections, you will add many more reflection points along which you can reflect in your group. And it turns out that any of these intervals appearing in this tiling of the real line is labeled by one of the group elements in the generators S and T. So here you see obviously T, because this is what maps your identity region to the right. Same on the left. And then it continues to the right with adding the generators in alternate ways, and to the left, it's the same pattern. And the different color of these fat dots, them being white or dark blue, tells you what the generator is that takes you from one side to the other. So here, to go from this section labeled T to this next section labeled T times S, you need a generator of color S on the right-hand side, and then one of T, and so forth. So we can label these vertices with the generators S and T somehow by color. And in general, this will be true for all the codimension 1 faces. They will be colored by some generator. So here, in this two-dimensional example at the bottom right of this side, you have 3 generators which correspond to the 3 triangles that are adjacent to the identity region. So here's S, T, and R, say. And then, okay, in principle, I would like to color the codimension 1 faces, which are these sides of the identity region, but it's easier to draw if I color instead their opposite vertex. So we have blue corresponding to S, which is this grid of vertices in the plane, and also it's the corresponding grid of codimension 1 faces like this. And then say T is the yellow ones, it corresponds to this face, and then this class of vertices. So the colored dots, the reflection on this plane, they preserve the colors of the dots. Okay, so if you have the third reflection R, it corresponds to the third class of vertices. And I could go on for a couple of minutes coloring in all the vertices, but I guess I don't have to do that. Okay, so the codimension 1 faces are colored. This is important for us later. And then the chambers of this complex, this Coxeter complex, which is the tiled plane, the tiled real line, or some other tiled R to the N. So the maximal simplices in these tilings, they correspond one-on-one to elements of this Coxeter group. So each triangle in the plane has a unique label by some W, I don't know, this one here, in this group. And then the words in the generators you can write down. They correspond to galleries in this complex. And by a gallery, I mean a sequence of triangles where subsequent ones share a face of codimension 1. Okay, so let's do an example for this little W here. So the way you get to W is you start at the identity, and then there's many ways, but let's do a minimal one. You walk over a codimension 1 face to an adjacent triangle, and then over another codimension 1 face to yet another triangle until you end in the triangle that's represented by W. And then you can read off a word for this element W by looking at the colors of the codimension 1 faces you just crossed. So going from the identity to the next triangle is stepping over a face of color gray. So that would be an R. The next step is a face of color blue, which was S. And then you cross a face of color yellow, and then another face of color gray. So here it's a gray vertex as well as here, which means that this last edge we've crossed is also gray. So that would be the word RSTR for this element W. And of course, there's many other words. You can take detours and go for non-minimal words as well. The shortest ones, they're the minimal representations of these elements. Okay, and we will use this feature. Okay. This is really bad. Next time I'm not gonna use so many colors and pictures. Okay, since I only wanted to write on that slide anyway, I'm gonna do it without the headline. So it said folded galleries and decorated words. So let me summarize. A gallery is a sequence of chambers. Oh no, now my writing disappears as well. I'm very sorry for these technical issues. Let me see. Here. Okay. So here gamma is a gallery. And I want it to be a sequence of maxima simplices. C0, C1, up to Cn, such that two subsequent ones have a codimension 1 phase in common. So Pi is a codimension 1 phase of Ci minus 1 and Ci. So P1 is a phase of C0 and 1, P2 is a phase of C1 and C2 and so on, and you end with codimension 1 phase Pn and the last chamber Cn. And then writing it like this, we have some extra information. We not only have the sequence of simplices we're looking at, but we can now read off a word which we call the type of gamma. And it's just a sequence of S's, where Si is the color of this codimension 1 phase Pi. And by color, I mean the generator that was labeling this codimension 1 phase. So from a gallery, we get a type, which is a word in our group, and we call gamma folded if it happens that some subsequent triangles are equal. So even if they're equal, we really want a codimension 1 phase that sits in between. So this notation we used for the gallery, even in the case where Ci equals Ci plus 1, in our list gamma, there appears a panel Pi plus 1 sitting in between Ci and Ci plus 1. So two galleries where the list of Ci's are the same, they can differ in case where two subsequent Ci's are equal, but we've recorded a different panel in the middle. So we really want this. And this is more information than that's typically used when you write down galleries simply as sequences of alcoves or chambers without recording the panels in between. Okay, let me do an example of a folded gallery. Let's look at this complex again we just had on the previous slide. So as I said, this gallery, and in fact this goes back and forth, can be given by some word. And if we start at the identity here with our gallery, we can think of it as like marking this maximal simplex, crossing over a codimension 1 phase to some other simplex, to a third simplex, and then maybe back. So here the identity would be C0, this one would be C1, this one would be C2, and C3 would be the same as C1 crossed over this panel, P2 being the same as P3. And here I would call this gallery folded at the panel P3, yes, because the C2 and the C3, they're equal. Okay. These folded galleries can be denoted by decorated words in the following way. So again, we list the colors of the panels we have crossed, but here, sorry, this drawing is wrong. So we end here in the same, oh no, now I have to say a word again. Okay, so we start here in Z0, move over to the right-hand side to the next edge, move over to the right-hand side to the next edge, but instead of moving over to the next, we stay where we are and repeat this edge. Okay, so C2 is the same as C3. And in our word notation, we want to write it in the following way, as if we could have crossed this blue panel over here, but we haven't. And since we haven't, we put a little hat on it, which should indicate that we omit this possibility of crossing at a panel of color blue. Okay, so this is different from the gallery that starts here, moves over to C1, moves over to C2, but then repeats on this panel, which would be denoted like this. Okay, so this is what I said earlier, that we really distinguish two galleries that record a different codimension 1 phase in between two subsequent alcoves. Okay, we have these galleries. There are these sequences of triangles, and we really draw them with these squiggly lines walking through the triangles one after the other, and they can be minimal, but must not be minimal. For now, later we will restrict to minimal ones. Okay, but I said I'd like to talk about orientations as well, and here an orientation, oops, let's use blue. An orientation is, well, morally, it's a way of making these folds more complicated and not allowing for some of them. But it's something that really comes up naturally later in the building's interpretation. But the definition is fairly easy and quite general. So an orientation on the Coxeter complex is a map that assigns to every pair of a codimension 1 phase P inside a simplex C a sign, namely just a value plus or minus 1. And again, in this example, in dimension 1, it would just mean that for every vertex, which is a codimension 1 phase, and every edge containing it, you decide whether this edge lies on the plus side or on the negative side of this vertex. You don't have to put pluses and minuses on both vertex. You could also assign 2 pluses at one vertex or 2 minuses, saying that both sides are positive or negative. However, it's more natural to do this in a periodic fashion, and for example, say that a direction at infinity, say this direction over here, induces an orientation. So Anne Thomas is based in Sydney, and Sydney's summers can be pretty hot, so she decided that the shady side should be the good one. That's why we assigned the pluses to the sides of a vertex, and we really think of these vertices as walls in which you reflect. So they cast shadows, hence the name of a shadow that's going to come later. And you want to sit in the shade. So the plus side is really like on the side that faces away from the sun, and the minus side is on the side that faces the sun. Similarly, you can do the same here in dimension 2. So for each of these walls and each panel inside this wall, you put a plus on every triangle that has a codimension 1 side face on this wall, and a minus, oops, sorry, on the other side if the sun you're looking at sits, for example, down here in this negative cone direction. Okay, so the thing you should remember is here that directions at infinity will determine sides of reflection hyperplanes that face that direction at infinity and sides that face away from this direction at infinity, which locally gives you an orientation of a panel in the sense that you can tell which of the two maximal simplices that are adjacent to this panel faces your direction at infinity and which side does not face your direction at infinity. And one thing we have to do later for technical reasons is to also discuss more complicated orientations at infinity that are not only associated with these cone directions at infinity that come from the spherical Weil group that sits on the boundary of this Euclidean Coxeter group, but also to regions that are somehow squeezed in between two adjacent hyperplanes and walk to infinity here. And what they correspond to is edges in a Euclidean reflection group that somehow sits at infinity of this two-dimensional Euclidean reflection group in the way where you project every reflection wall to a point at infinity, and you say they're connected by an edge whenever they are parallel and next to each other within the tiling of your two-dimensional reflection group. So there's a way of making sense of this in terms of dual compactifications of the Euclidean plane. Yeah, but I won't go into the details here. Okay, so upshot is there's many natural ways coming from the Euclidean reflection group itself to impose these local orientations on the panels and pairs of panels and maximal simplices. And all of these natural orientations, they're braid invariant, which means that if you pick an element in your Coxeter group and take two different words for it and have it folded, then those folds will be either all on positive sides or all on negative sides for no matter which word you picked. So there's these braid moves on words in Coxeter groups, and these orientations, they're well behaved with respect to these braid moves. Okay, lots of technicalities there, but let's eventually get to the definition of a shadow. So here it is. You take a reduced expression for an element in a Coxeter group, and you pick one of these natural orientations we have just talked about at length on the previous page. And then the shadow of this element little w in your Coxeter group with respect to that orientation is given by the ends of all positively folded galleries of that particular type. Let's do an example. Let me see. Okay, so here's a very explicit example. We take a reduced word, which means we take a shortest possible gallery from the identity, which is here, to this little w. It's not so little. To this w over here. And then we fold it. And by folding it, what I mean is if I write this as a word in the generators, which tell me the panels I cross with my gallery, then I'm allowed to put these heads everywhere, which means that I can omit a crossing in this gallery. And geometrically, this corresponds to really folding the gallery at one of these reflection hyperplanes. So if I would omit this last crossing here for my gallery, what would happen is I would not end up in W, but I would end up in its neighbor along this face here. If I would omit this crossing, but keep this one here, then I would repeat this little triangle. So the gallery would be the reflected image of this last bit here and would end up in this little triangle over here. And then if I omit both last crossings, then I repeat this little triangle. Let me outline it in red. I'd repeat this little triangle 3 times and would have a word that ends with 2 letters, both of which have a hat on them. And if you keep doing this, you will fill out eventually all of the gray little triangles in this picture. So here we allowed for hats everywhere, which means folds everywhere, but this is nothing but the Brüher order interval between identity and this little element W. So this is this gray set, which tells you that if phi puts plus everywhere, then the shadow with respect to this particular phi, that is the trivial positive orientation, so everything's allowed, is nothing but the Brüher interval. Okay, so in general, imposing these, this extra condition of being positively folded and not allowing folds everywhere, but only in directions that repeat maximal simplices on a positive side with respect to that particular orientation, will give you some subset of the Brüher interval. So in the middle, this is, for example, illustrated for the sun sitting above here and folding everything away from the sun. So let's do a baby example here. So this gallery, for example, may be folded here, which shields this, because all these folds are along hyperplanes where the plus side faces away from the sun that sits up here. Okay, on the right-hand side, you see that the shadow looks even more complicated if you have one of these skinny strips here playing the role of defining your orientation. So these things here, they're called chimneys. They've previously appeared in work by Rousseau or also Capras and Recursive in the context of compactifications of buildings. But they here also play a role in defining these orientations and shadows. Okay, so Brüher intervals are, as we've seen, special cases of these shadows, and they have recursive description. And together with Marius Gräber, I was also able to establish a recursive description, which really boils down to exactly the Brüher order recursive description in the particular case of a trivial positive orientation. And it's written here. So we don't have to digest the precise statement. Let me just mention that you have to distinguish cases where the elements, the generators are either in the left descent set or in the right descent set of your element X you start with. And then making your element shorter, you can compute the new shadow out of the old one by just multiplying the whole triangle picture with an S on the left or an S on the right, depending on whether you're in the left or right descent set. So it's really geometrical. You locally just stare at your triangle and see what the generator does to your element, and then you decide whether you want to go that step or not. So this is really like a hands down proof. And then this theorem generalizes to these chimney orientations, and this is joint work with Milicevic, Naqvi, and Thomas again. Okay. So here comes the connection to buildings, and luckily, Mike Davis has already said a lot about buildings in his beautiful talk yesterday. So let me just tell you that the one-dimensional affine buildings, they're just the infinite trees. So trees, graphs without cycles and no leaves, all of them are examples for buildings. And in the case where you have a regular tree with the same number of branching at every vertex, you're in the lucky position that this tree also has a very nice algebraic group attached to them. And I've pictured here the case of the tree associated to SL2 over the two adic numbers. And recall this decomposition of SLN we've looked at the very beginning of this talk into these three groups UT and K, where T are again the diagonal matrices, U the lower triangular ones, and then this maximal compact subgroup K, which has also a very nice geometric interpretation. Namely, you can think of K as being the stabilizer of a chosen origin, and here you're really free to choose whatever vertex you want as your origin. I've indicated it over here. It's this yellow vertex labeled 0. And in the automorphism group of the color-preserving automorphisms of this tree, the stabilizer of this origin really is the K here. Okay, so we have these trees, and in these trees, we have retractions. Okay, there they are. Here's the first type of a retraction. It maps the whole tree on one of the Coxeter complexes, which is this tile real line, and I've chosen this one, this horizontal real line, to be my favorite embedding of a real line in this tree, by just flipping all the other branches down to this horizontal line from a certain, from the viewpoint of a fixed edge. Okay, this is indicated by this blue arrows. And then it turns out that the taking pre-images directly links to this group K we've seen. And then there's a second type of retraction that somehow starts at a point at infinity, which corresponds to this sun we had chosen for the orientation on our horizontal line down here. And it flips everything over to the right, away from this sun at infinity. And again, it's linked to this other group appearing in this decomposition, namely the U, when you take pre-images under this retraction here. Okay, and then one can prove that this convex hull that appears in this Schwer-Horn theorem, which is the projection onto T of the left K orbit of little t, that this is nothing but one retraction that comes from infinity applied to a pre-image of this other retraction. And really, the idea here would be that you take a gallery here, then with this taking this retraction coming from infinity pre-images, you can really lift up this gallery into the branches in many ways. And if you then, that would be the red one. Oh wait, now I've messed up colors, I guess. Okay, let's take the yellow to indicate this here. You will see that they get mapped down again by this other retraction. And now the yellow things, they're really the folded galleries. Okay, so what these pictures hopefully illustrate is that by taking pre-images under one type of these two retractions and images under the other type of these two retractions, you will somehow automatically produce folded galleries. And this is actually how you prove that this certain double coset that appears up here is non-empty, which turns out to be the same question as some element being contained in this convex hull, which was exactly this set we were after in this projection. Okay. And then you can generalize this. Maybe I'll skip over this. Let me just tell you that for the chimneys, there's also more complicated retractions associated to those. So there's not only two types of retraction, but actually infinitely many types of infinitely many kinds of retractions in the building, which all have a very nice uniform description, but for which also there are somehow analogs of this Schwer theorems we were able to establish last year. Okay, let me really quickly mention some other places where these folded galleries pop up. I think they were introduced even by Gossin and Littleman in their study of highest weight representations of semi-simple algebraic groups. And then Guericke used them to characterize MV cycles, which are also an object in representation theory, and the MV polytopes that are attached to them. And then there's the theorems of problems A and B I've told you about. Okay, let me finish this talk by mentioning a bunch of open problems and questions I'd like to answer. So one thing we don't have at the moment is closed formula descriptions for the shadows. So for example, for this red set of triangles in this left-hand side pictures at the bottom here, we have this recursive description, but we don't know, like on the nose, if you give me an element, how to check whether this element is red or not. That would be nice to have, like a closed criterion that tells you, are you in the shadow or are you not in the shadow? Then, as I've said, if you impose the trivial positive orientation, so all folds are allowed everywhere, then you get back Brüher order. Are there other orders that can be defined using these shadows? So looking at pictures, one can see that these patterns are actually nested. So if you start with an X that's closer to the identity than the one for this red picture on the left, you will see that for many smaller or even larger X's, you will produce patterns that look similar to the one you have here, and you can actually fit this red pattern inside these larger pictures, or vice versa. If you created a smaller one, then it fits in this red one, and it would be really nice to use these like picture intuition turned into a proper definition of new orders on Coxeter groups. Then we would like to characterize what we call co-shadows. So for the shadows, we've fixed an element and folded it and checked what we can get. But you could also ask the reverse question, pick an element and ask for which other elements are actually out there, so that your favorite element is in their shadow. It's like you want to know like the larger galleries that fold onto your gallery. This is really related to this picture on the right-hand side. And then I told you in the beginning that you can fit this red picture into this gray picture by picking a ship and then coloring in the triangles here. Well, we can actually do this on a picture level, but we haven't understood why this works algebraically. So that would prove, if you can do this, this would be to establish a formal relationship between the shadows and the co-shadows. But for that, we would first need a better understanding of the co-shadows in order to actually prove that there's a formal relation. Okay, I'm sorry I went over time, but I hope I haven't stressed your patience too much. So thank you for your attention.
Well, let's unmute and thank Petra. And she didn't run over. She started slightly late. That was perfect.